All right, so today we're going to talk about null spaces, column spaces, and linear transformations. This These concepts are really not new, and it's going to be the same math that we've done before. The thing that will be new is really just these concepts and the definition. So what is a null space? It's the set of all solutions, and when we write these solutions, we're going to write them parametrically to a homogeneous equation, ax equals 0. So what vectors and what format are they going to take? Can I just make any vector if I have a matrix A? Can I choose any values for x1 and x2 and x3 where I get out 0? And that answer is kind of obviously going to be no, but what are they going to be? So, and that is the theorem that we have. We have the null space n by n of a matrix, and it's going to be the number. This is going to be the set of solutions to the system ax equals 0. And it's really the same thing that we have. And it's going to be a subspace of Rn, where n represents the number of columns that we have. We're not saying that it's going to have n vectors, and we're going to find out really quickly like how many vectors we're going to have in our subspace. Whoops, hit the wrong button. So it's going to be a subset of Rn since n has n columns. Let's verify the properties A, B, and C that we have in the book for that one. So let's look at, and this was in 4.1, what makes a subspace. And I won't be asking you to do these things on any test or quizzes that I give you, but it is good to look at them. And what are those three properties? So the first property is that 0 vector exists in the null of A. And this one will be pretty easy to prove, but let me just change one thing on that one. So the first thing is that the 0 vector is in the null of A. Okay, so basically when I take this and if I have A times that 0 vector, I'm going to get out 0. And the second thing that we have is that any other two vectors that we have, we'll call those two vectors u and v, are also in the null of A. And that's just saying that A times u equals 0, and so does A times v equals 0. And then the third thing that we have is that it doesn't matter what that constant is. C times 0 also equals 0. And those are the three things that we have to prove that something is a subspace. There are some good examples about what makes a subspace and not a subspace in that first section. So we're going to start off the way we do a lot of these things. Homogeneous equations, you can augment and then row reduce that thing. In the notes, I kind of did it by hand, but what does it look like when we get this? When we row reduce this thing, and how do we interpret this thing? And so kind of obviously this is going to be x1, x2, x3, x4, and x5. And we can kind of imagine what equation number 1 looks like and what equation number 2 looks like. And can I choose anything? So obviously if x1 and x2, x3, and x4 all equal 1, that doesn't equal 0. That would be a basic example. But when we row reduce that, what are those values going to be? Are they dependent upon each other? Can they be anything? And obviously in this case they cannot. But we obviously see that the 0 vector does exist in it. If x1, x2, x3, and x4 all equal 0, then A times 0 does equal 0, right? But what do they look like in general? And that's the question that we're asking. So when we row reduce this thing, we get 1, 2, 0, 13, 33. Those are the values that we have for the coefficients. And then 0, 0, 1, negative 6, negative 15. Whoops, negative 15. We augment that with 0, and we know how to read what that matrix says. And that just says that x1 plus all those things equal 0, or x1 is equal to negative 2 x2 minus 13, x4, minus 33, x5. So we can kind of see already what the three free variables are. Try to change color. There we go. Did get that color changed on that one. Those are the three free variables that we have. And x2 is free, so that equals x2. x3, we're going to get that one from, so we got x1 from the first row. x3 we're getting from the second row. And that equals negative x3 plus 6 x4, once I move that over to the other side, plus 15 x5. So writing this thing parametrically, we want to know what all 5 of our variables looks like. x1, x2, x3, and that is the general form of our vectors, of our solutions. And then if I factor out the x2, the first free variable that we have, x2 is negative 2 x2. Sorry, x1 is equal to negative 2 x2. And then we could write this thing horizontally or vertically. x2 is equal to x2. x3 doesn't have an x2 in it. x4 doesn't have an x2 in it. And x5 doesn't have an x2 in it. Whoops, that should say 5. And I'm just going to write that, just remind myself over here that x4 is equal to x4 and x5 is equal to x5. Those are the three free variables that we have. So now, and then the second free variable that we have is x4. x4, we have negative 13 of those in terms of x1. x2 doesn't depend upon x1. x3 has 6 of those, 1, and x4 does not depend upon x5. So we are kind of just going to have that. And then the last variable that we have, one of these days I'll get used to my pen, but I think I can blame it on the pen now that I'm doing distance, and not just on my bad handwriting. So those are the three vectors that we have. So the null of A is going to have 3 vectors in it. Those vectors are negative 2. I'm just writing that again. 0, 0, 0. The second one is negative 13. 0, 6, 1, 0. And of course, I encourage you, if you don't like this handwriting, please look at the other videos that I'm posting of my colleague. She has much better handwriting than I do. Her videos are just as good or better than mine. So the spanning set of the null of A. It's going to be, those 3 vectors are going to be linearly independent. So if we just look at those, you really can't tell just by looking at them, but those 3 vectors are linearly independent. We cannot use, for example, these 2 vectors to get that third vector. We can obviously see that, those are not just a combination. We can't multiply that by 6 and some change. We can multiply negative 2 by 6 and some change to get negative 13. But you can't multiply 0 by 6 to get 6. That doesn't work. And some change. 6.5. So those are going to be linearly independent. So the 3 vectors that we have, the value of the constants that we're looking at right here, the weights, are going to be whatever we choose for x2, x4, and x5 are 3 free variables. If the null of A doesn't equal 0, the number of vectors in the spanning set for the null of A equals the number of free variables that we have. So that's saying we're not looking at just the 0 vector. The 0 vector is in there. So the number of vectors that we have depends upon the number of free variables that we have. That is the observation that we have for the null of A. The column space of an n by n matrix is a set of it's just breaking apart the columns of A. That's really all that is. That would be the column space of just A. So, and it's just those vectors, n vectors that you're going to have in there. So that's what the column space is. If the column space of an m by n matrix is going to be a subspace of Rm. Now, what does m depend upon? It depends upon the number of equations that we have that is represented by matrix A. So recall that if AX equals B, then B is a linear combination of A. Therefore, the column of A is going to be the vector B. It's going to have a solution. And that's really what we're looking at for all of those. What is the solution for AX equals 0? If it doesn't equal 0, then what is the general format of the value of the variables so that AX equals B? Is there only one solution, or are there a number of solutions for that? And so we're going to look at that in our notes and in our examples. So find a matrix A such that W is made up of the columns of A. So basically, what is the span? How do we break those apart? Well, what two variables do we have? Well, the two variables that we have are X and Y. Okay, so W is made up of those two variables, X and Y. And then we're going to put those two things together, and we're just going to change this. Whoops. I can't change my color. There we go. Got the color changed on that one. So it's this span. Actually, I probably shouldn't have closed that out right there, but it's okay. I'll fix that later. So X has, in the first row, we have 1 X. In the second row, we have 0 X's. In the third row, we have 1 X again. And looking at the other, and looking at how we can express Y. Well, we have -2 Y's in the first row. We have 3 Y's in the second row. We have 1 Y in the third row. And that's going to be, X and Y is going to be an element in the reals. So, so that, now we can close that bracket right there. So that's just how, that's the matrix A. Such that, and so our matrix actually is going to be, so A really is, that's our coefficient matrix. So the coefficient matrix for this one in terms of X and Y is 1, 0, 1, -2, 3, and 1. And our two variables that we have are X and Y. And we can just say that that's going to be times X and Y. And when we multiply A times X or A times U, we get out W. So A times U is how we express what W is. That's really what that is. Those are the columns of A. The column space of an n by n matrix A is all of Rm if and only if the equation has a solution. So when we're looking for a solution, we're looking for no foolishness. That's really what that means. Okay? We're looking for, what does that thing look like? So the columns of A are going to span Rm. And M is a number of equations. And so we can still, R2 is going to be, it means that it spans, I can get to any point in our 2D world. R3, I can create vectors and that'll get me to any point in the 3D world. And that's what it means for the column space, to span all of those for the solutions of AX equals B. So is W in the null of A? Is W in the null of A? So what does null mean? And it's really, as I said before, when I see null of A, what that means is that A times X equals 0, or in this case, A times W. So we can use our calculator and or do it by hand. Does A times W equal 0? That's what we're asking. And so I am going to pull out my calculator and just say, well, our calculator gives me out the vector 0, 0, 0. That's what A times W is. A times W equals the 0 vector. Boom, it is in the null of A. So that answer to that question is yes, it is in the null of A. All right. So does A times W, is that in the column of A? So that is just saying that does A times X equal W? Does it have a solution? Right? Does it have a solution? So the way we do that is we're going to take our matrix A, augment that with W, and see what happens. So when I augment that with W, our A matrix is 5, 21, 19, 13, 23, 2, 8, 14, and 1. So now I'm going to augment that with my W vector or matrix. We have 5, -3, and 2. So do we have a solution? Is there foolishness? If there is no foolishness, then it's going to work. And so when I row reduce this thing, use what we use, the main tool that we have, our row reduction method, or Jesus, and that gives me -2/9, if I can read my handwriting, when I augment that, when I throw that in the calculator. And that's going to be +1/3, and that's going to be -8/9. So yes, is W in the columns of, yes, it is, as long as our X, and now we know what X is. X has to be X1, X2, and X3, has to be these 3 values. No values are free in this one. So if I plug in -2/9 for X1, plug in 1/3 for X2, and -8/9 for X3, then that's the way I'm going to get to this point in space. So that is it, the contrast between the null of A and the column of A. So the column space of A is a subspace of R of K. So the column space, where K is equal to, in this example, the number of rows. It's a subspace of Rm. Okay, and in this case, we have 4 rows. And that's how you find the column space for that one. The null space, where K is going to be 3. That's going to be the number of columns that you have. And we were talking about an m by n matrix. So that's going to be K is equal to n. For any, find a non-zero vector in the column of A. So what do we want? So there are many possibilities that we have. So you can choose whatever you want to. We're asking for we can use those 3 vectors to get another vector. And it's going to have 4 entries. That's why it's going to be a subspace of R4 or Rm. So it doesn't matter what you choose, right? You can choose C1, C2, and C3 to be 0. Therefore, we're going to get out 0. We can choose C1 to be 1 and C2 and C3 to both be 0. And if I do that, I get out 1, 2, 3, 0. That is a non-zero vector. That is a way that I can get to 1, 2, 3, 0, right? And you can choose lots of possibilities, and you can do this forever and ever and ever. You can make up your own possibilities. You set them all equal to 1, and that first entry is going to be 6, 13, 19, and 1. So that's how you get to that, a vector with those 4 entries. I'm not saying you can get to any for a valued vector. I don't know whether I can get to any point, but maybe I can. We're just asking what those, how do we get to a couple of points or a couple of vectors in that one, okay? Find a non-zero vector in the null of A. So we're going to do this the same way, null of A. We're saying that I have to get out 0. So this is saying that x1 is equal to -2x2, and x2 is free, and x3 is 0. So How do we do that? Well, we can let x2 is free. It can be whatever you want it to be. And in my, in the notes, I said that x2 is 4. So if x2 is 4, then we already knew that x1 was negative. I'm just rewriting what is on the other slide. And x3, well, x3 has to be 0. X3 has to be 0 because of our augmented row reduced matrix, and x2 is 4, and now this has to be -8. So x2 is free, so you can choose it to be whatever you want it to be. So that is a non-zero vector in the null of A. So what that means, if I take this vector and I take our given vector, given matrix A, and I multiplied it by x, I'm going to get out 0, 0, 0. Whoops. And one more 0, excuse me. That's what I'm going to get out. Yep, that was a 4 by 3 originally. So A times x gives you 0, with x being that, and A is given. And I'm not going to rewrite that. So that's what that means. That's the null of A. The contrast between the null of A and the column of A. Now the thing that's kind of, I don't know, counterintuitive for this one, we're talking about columns. It's going to be the subspace of the number of rows that we have, okay? It's the subspace of Rn. It takes time to find those vectors in the null of A, to find each one of those, and that depended upon the free variables. It's easy to find the vectors in the columns of A, just split those apart. No obvious relationship between the null of A and the entries of A, because you have to find those free variables. There's an obvious relationship between the columns of A and the entries of A. It's just you are just splitting them up. How many things do you have in each of those vectors? Well, you have the number of rows in that one, going back to that one. If A times V equals 0, if you chose correctly, then you're going to get out 0, and that vector is going to be in the null of A. If you have a solution, it doesn't have to be unique. If there is a solution that exists, that's going to be in the column of A. It's easy to tell if V is in the null of A, just multiply A times V. To find out whether or not a given vector is in the column of A, you have to row reduce A times V, and do you get foolishness? If you get foolishness, then there is no solution. The null of A is equal to 0 if and only if. Null of A is only going to be the 0 vector, has only the trivial solution, which means there are no free variables. Null of A is equal to 0 if and only if the linear transformation is going to be 1 to 1. If it is there, can you choose any vector? Okay, that's what you're going to do for the columns of A. So that's kind of it. So to find out whether or not a subspace is a vector space, V is going to be a subset of H, and it goes back to A, B, and C, really from 4.1. Is that 0 vector? Is that in H? For each vectors, if you choose 2 vectors, to find out whether that's a subset of H, if U plus V is still going to be in H. It's going to be closed under addition. If you choose each U in H, then if you can multiply that by anything that you want to, it's still going to be in H. So going back to that example from the null of A, so once I had one vector that I think it was 1, 2, 0, 0, 0, multiplied it by 12, right? Some scalar. And I still got out the 0 vector, 0, 0. So if the subset H satisfies those 3 properties, then it's going to be a vector space, okay? It's going to be the span. Span is just a fancy name for a solution. The set of all our solutions for either the null space or the column space. The null space is always going to be a subspace of Rn, just going back to, again, to the review, and that represents the number of columns that you have. And that's going to be a subspace of Rm, the number of rows that you have, the rows that exist in A. So determine whether or not the following sets is a vector space, or provide a counterexample. So is that going to be a vector space? So, so we have two random variables, but we have this restriction upon it. When I take those two values, x is going to be 4 more than y, right? So that answer is going to be no. That answer is going to be no, because you cannot, the zero vector does not exist. So the zero vector doesn't exist. That's it. It just fails part A. Okay? You can't, if you set, yeah. If you set x to be 0, then y can't be 0. If you set y to be 0, then x can't be 0. So you have to have that zero vector in there. So now we have 3 vectors in here. So what does that kind of look like? But we have these restrictions right here. So x minus y equals 0. So what that says is that we have 1, -1, 0, and then we have the 0 vector. We'll just kind of augment that. And the other one that we have is we have y plus z equals 0. So we can, the first thing that we can check, A, and actually we'll just say, boom, we'll actually do x, y, and z. Does that give you out the 0 vector? So when I multiply those two vectors, do I get out the 0 vector? That answer is yes, we do. And 99% of the time, if that 0 vector does exist in there, it's going to be a subspace of it. Okay? So it's going to be closed under addition. And what is it a subspace of? This one right here is going to be a subspace of R2. Okay, because we have two equations in essence. Okay, and that's kind of it with that. And now all we have now we're going to write out the column of that. All we have is S. So we have two variables, x and y. So if x, y, I accidentally just copied and pasted in z right there. Those are any real numbers. So does the 0 vector exist? Yes, it does. So 0 plus 0, I'm just choosing x and y to be both 0. Does that give you out the 0 vector? And yes, we do get out the 0 vector. So, but writing this, what S is, in vector form, we have 1, 2, 0, and we have 1, -3, +3. Okay? And if I would row reduce this, I wouldn't have any foolishness. I can make that thing equal 0. There is no foolishness on that one. There is a free variable. So the 0 vector exists. And what is this going to be a subspace of? Well, how many entries do you have? You have 3. So it's going to be a subspace of R3. 1, 2, 0. That tells you how you're moving in those 3 directions. So that's why that is going to be a subspace of R3. So the last one that we have, probably not going to ask you many questions about the kernel or linear transformation, but a kernel is honestly just a fancy way of talking about the null space. So I'm going to go through that one real quickly. And if it's a linear transformation, we've done those things. And what makes a transformation linear? And we still have these similar properties that we have. It's closed. If you add the two vectors together, then do the transformation, it's the same as doing the transformations independently of each other. And then it's closed under scalar multiplication. So that's what we have right there. So the kernel or the null space of that transformation is a set of all vectors that give you out 0. The range of t is a set of all those vectors in the form tu, where u is still in V. So the transformation is the same thing as multiplying it by the transformation matrix. Remember, we call that our transformation matrix. That's what that is. So if it is linear, then we can make up a transformation matrix that will give us some values. All right, so let's look at this example. So we're taking something that has 4 variables and we're knocking out 2 of them, and we're going to put this thing from subspace of R4 to R2. And so the way we're going to do that is we're going to make up a new thing. So we're going to add these first 2 variables together, add the second 2 variables together, and that is the way we're going to get out the 0 vector. And what do we know about x and y? Do they have to both be 0? No, they just need to be opposites of each other. So what forms do they look like? So we've already answered like the question of what do they look like. Well, it's already telling you that we're going to add those first 2 variables together, get out 0. We're going to add those second 2 variables together, and we're going to get out 0. So what do they look like? What they look like, well, x has to equal negative y, and z has to equal negative w. So that's what they're going to look like. It's kind of it. So that's going to always give you the null space. So those vectors are going to look like x, negative x, and z, negative z. That's the form that those vectors are going to take, right? So that's what we have for that one. It's the form of those kernels. So what is this one saying? So the kernel is already telling you that they have to, it's asking you what is the null space. So we're taking something that lives in 3D world, and we're going to knock out one of those variables. And can you get to the kernel? Can you get to that 0 vector? So it's already telling you, can we get to that 0 vector? And the answer to the first one is yes, we can get to the 0 vector that's just going to have 2 zeros in it. And that is going to be, we're just knocking that one out. And so therefore that can get you to that 0 vector. That's going to be yes. So the kernel for the next one of 2, negative 3, 4, if I just knock out one of those variables, then I cannot, because I'm still going to have a 2 and a negative 3, right? So we knocked out the first one, the last variable, excuse me, and we still had those first 2 variables, first 2 values left over. For this one, no, we cannot, and that is not in the kernel of L. So is W in the null of A? So this is going back to really all in one, and it's the same as that first example, honestly. So we're asking the question, does A times W give you 0? And we take out our calculator. And if A times W equals 0, that answer is yes. If it doesn't equal 0, the answer is no. And pull it out of the calculator, and we got the answer, yes, it does. A times W, that's A and that's W, that equals 0. Is W in the column of A? And so basically, we're going to take this and we're going to augment A with W. We're going to row reduce this thing. And do we have a solution? So we're going to ask that question, do we have a solution? Is there foolishness? If there is foolishness, W is not in the column of A. And then when I do this, we get out that this vector 0, 1, 1, negative 1/2. 0, 1, 1/2, 1, and 0, 0, 0, 0. So the first 2 rows, I was still in the running for it not being in the column of A, because this is telling me that I had a free variable. But since I have this 0, 0, 0, 0 row, there is no foolishness. And 0 always equals 0. If that last value was not 0, then it wouldn't be in the null of A. And I'm not asking you like what the solution is, though we could write it. And actually, I will write it just for practice. So we have 3 variables, x1, x2, and x3. And so we're going to express this in terms of our free variable, which is x2. Oh, and then we have we have some constants that we have to worry with. So x1 from that first equation is going to be equal to negative x1. x2 is equal to x2. And, oh, I apologize. That should be x3. So -1, 0. Oh, x2, sorry, is equal to -1/2 x3. And x3 is x3. And then we have these constants that we have. So these are going to be plus -1/2, 1, and 0. Okay? So that's the way we're going to express that. And that can be, you can now choose whatever you want to. And those would be the values of x1, x2, and x3. And that's it for section 4.2. Please do your homework. Look over those. Make sure you understand the difference between the comma space and the null space.